Alright, let's find the area bounded by this curve on 0, 1. And I don't just mean any area, I mean the exact area under the curve. So the cubic looks something like this. I'm going to exaggerate it, make it large. It's from 0 to 1. So we're going to split this up into ... an infinite number of subintervals. And so let's say the first one, let's say we're going to do this and this. So I've got some rectangles going here. So let me do this in theory and then in this example. So as we said, we're going to take the limit as n approaches infinity. And we're going to sum up all of the rectangles from 1 to n. Let's see if I can get this in a little better. 1 to n. And in general, we're going to take the evaluation. Say, I don't want to use x again. Say that the width of each of these subintervals is change in x. And the height is going to be on the function f. And it's going to be evaluated at these various spots. I call them c for constant. Say this is c sub 0, and the first one is c sub 1, c sub 2, c sub 3. I can't write this small, but I'm going to come across and get c sub 1, then an increment c sub 2 times change of x plus c sub 3 change of x times c sub 4 times change of x. And so it goes on till it reaches n, but n is going toward infinity. So in theory, you should be able to see that this is the exact area under the curve, taking the area of an infinite number of rectangles. All right, so now for this specific example, what is our change of x? Again, in general, change of x is always, like this interval is a to b. So we're going to take, to get the width of one of the subintervals, it's going to be b minus a divided by the number of subintervals. So n. b minus a over n is change of x. What about f of ci? Well, c sub I is always going to be starting at a and adding I times change of x. Do you see how that's true? So the very first one, if we're starting at 1, we are going to start, in this example, a is 0, and we go over to 1 change of x. So that'll bring us here, and we'll evaluate that at f. Then we'll go over to 2 changes of x's plus a. So that'll bring us over to the second one, and 3 changes of x's, and 4 changes of x's. So this will always work for any examples. An example. So I'll kind of box this up. All right, so we'll keep that in easy retrieval storage. Now let's actually do this particular one. The n goes to infinity. As n goes to infinity, the summation, I goes from 1 to n. And what is our change of x? Well, b minus a, b is 1, a is 0, so we're going to have 1 minus 0 over n. So our change of x is 1 over n. So this part is taken care of right there. Now this part, since the function is cubing everything, I'm going to take a plus I change in x, and change of x is defined already in this part as 1 over n. So change of x is 1 over n times I is I over n, and a in our example is 0. So I have I over n. Again, that all came from knowing what change of x was and what a was. And this is cubed. Alright, so now all I have to do is simplify that. And hopefully I will find one of our keys in the middle of it all. Alright, so simplifying that, I am going to combine these two, and I'm going to get the summation as n approaches infinity of, oops, I always do that. Why do I do that? I'm sorry. The limit as n approaches infinity of the summation as I goes from 1 to n. And in here, I'm going to change that to I cubed and n to the 4th. Alright, now this summation only deals with i's, so I think that I will pull that across the summation sign. It's not across the limit sign, but this n is not affected because by this summation, because there's only increments i's, values with I in it. So I can pull that across the summation sign. And so I just took that over there. And then I have left I cubed. And there, sure enough, is one of our keys. So if you look back, I cubed was one of them. So I'm going to come down on this and keep going. So I'm going to have the limit as n approaches infinity of, instead of I cubed, I'm going to go back to one of the keys, and I cubed was n squared plus 2n plus 1 over 4n squared. And no, it was, actually I have to look. It was I cubed is n squared times I cubed. Where is it? Why didn't I write it out? Okay. So I cubed, we have this 1 over n to the 4th. Now I am taking the summation because I know the summation of I cubed. And the summation of I cubed was n squared times the quantity n plus 1 squared over 4. Alright, so I used the key. Alright, good enough. Now I'm going to have to multiply this out. So this is n squared plus 2n plus 1 times n. So I'm just simplifying, following my mathematical nose where it leads. So n squared times all of these things, and I have an n to the 4th. I guess I'll combine that first. It seems like it'll be simpler. So then I have n squared plus 2n plus 1 from squaring this, and then n squared from simplifying this, and then a 4. Alright, so next, since I remember how to take limits as they approach infinity, I end up dividing each of these terms by this. So I get the limit as n approaches infinity of n squared over 4n squared, dividing this 2n over 4n squared plus 1 over 4n squared. So I can take this cancels and I get 1 over 4. So the limit as n approaches infinity of this term is 1 over 4. And you'll recall that this simplifies to 1 over 2n. And as n goes to infinity, the denominator gets infinitely large. This whole expression goes to 0. And same for this one. So I got 1/4 for my answer. All right. So that was pretty cool that we have the exact answer of the area bounded right in here. This area is 1/4. All right, let me have you try one. If you would kind of follow the logic that I just did with that one, we can do a you-do. And I want you to do y equals -x² plus 6 on the interval between 0 and 2. So I want you to look for one of our keys to pop out. So algebraically manipulate, and first of all you're going to substitute in from your box, and then you're going to try to manipulate it in order to use one of your keys. So one of these ought to pop up somewhere in your work. Alright, so you get started on that one and bring your work to class as far as you can go, and we will put our heads together and see what we get. Alright, so that's it for numerical integration. More Riemann sums. Alright, till tomorrow. Goodbye.